Okay, Chan, physics, last thing for you guys until you get to the Coulomb's law practice. So, what is Coulomb's law? So, first of all, we understand this is a name of the scientist who came up with this law. So, that's Coulomb himself. And what is Coulomb's law? So, Coulomb's law says, let's see if we can get this to work here, that there's going to be a force between two charged particles, right? And so, first of all, we have to look at what's an electric field. So, if we were to look at these two charges, one's positive, one's negative, then we would think that they should be attracted to each other. They're opposite and they should be attracted to each other. And the question becomes, okay, what does that look like if we could draw it out? What do those forces look like? And the first thing we have to do is say, okay, if we were to somehow map out what the forces look like between those two objects, when they were right in the middle here, they would be really, really strong. The force between them would be really, really, really strong. But then as we get out further and further and further away, it would be less and less of a of a force. And so we call that an electric field. And what we do is we say, okay, let's pretend like if we could find this little positive charge, if we could just find a little positive charge that we could put right in here, what would happen to it? Well, we would know that it would be pushed away from this positive charge, so it would be pushed this way, and it would be attracted towards this negative charge right here, so it would be pulled that way. And so the positive charge would move from this to this side. And so if we were to map that out, we would say, well, that then the electric field would go from positive to negative. And if we were to map it out, it would look like this. So if we look at this little chart right here, anytime if we were to put a positive charge anywhere in these spots, like right here, or even right here, that charge would then move this way. And so this would be our positive charge, and this would be our negative charge. And so the field goes from positive to negative. And you can see them like the positive charge would be attracted at any point right here. It would be repelled at any point right here, and then it would be really, really strong between the two of them as they would come together. So Coulomb figured this out, and we had to admit that this has to happen because when we had the ball hanging from the ceiling or when we had the can, there's gravity, and we know that from Newton's second law, nothing should move unless there's a force acted upon it. There's a net force, and so that the inertia of that can, the inertia of that ball hanging from the ceiling should say it shouldn't move unless there's a force. And so when we create that positively charged on the PVC pipe, or when we charge anything, then we're going to create a force between those two objects. And it's either going to be an attractive force because if they're opposite, or it's going to be a repelling force if they're negative. And so Coulomb came up with this and said, okay, well, I know that this is true, and I'm going to see if I can come up with an equation for it. And so before we come up with the equation for it, we can just say, okay, what do we know for sure? So if we had two positively charged particles and we had them d apart from each other, and then we pushed them 2d apart, so we double the distance between them, we would know that that force wouldn't be all that great. We had to get the PVC pipe really close to whatever we were trying to do to actually get it to move. So the distance has to have something to do with it. And so if we were to say which charge pair has the largest electrostatic forces acting on it, well, the answer would be the first one, right? Because the closer they were, they must have a much greater force, because that's when we got things to move. When we were far apart, it didn't do anything. All right. And so we also know that, like, if we really wanted it to work really, really well, we took the rabbit's fur, we really, really put a lot of electrons onto that PVC. So if we added more charge, then we could get a better reaction. And so this is an example. What we see here is, but they decided they're going to call charge with the letter Q. Now, I know it doesn't make any sense, but there's a lot of C's, there's a lot of M's in physics, and so they decided to name charge with the letter Q. So in this first one, it says the Q is -4 microcoulombs. That's that little U right there. That's a micro. That's a metric term. So we have a milli and then a micro. And so milli would be -3 and micro would be -6. And so there's -4 microcoulomb charge on that first one on the left, and then a +4 microcoulomb charge on the one on the right. And then if we had a different one where we had an 8 microcoulomb charge and a 4 microcoulomb charge, what would the difference be between the forces? And so we know that if there's more charge, then we got more of a reaction. And so we would think that, of course, if we had more charge, the forces should be greater. And they are. Okay, and so we know that the equation must have to do with both how much charge is on the object and how far apart they are. And so what's really, I think, great in physics is every now and then something shows us that maybe we're right on track. And so if you look at the equation for Coulomb's law, which is this one right here, F is equal to K Q1 Q2 divided by R squared, it looks really similar to that same equation that we just got done with gravity, where we had a constant, and so K is a constant. And you guys, I'm not sure if everyone's got this yet, but we're going to try our best. A constant is a number, and what happened was Coulomb was saying, well, it had to do something with charge, it had to do something with the distance between them, but every time he calculated the force, it was a little off. And this time it was off by what we call K. So he adds this constant, he adds this number into the equation, and then everything works out. The same thing happened with Newton with gravity. He said, well, I know it had to do with mass, it had to do it with the distance between them, but they were always wrong. And so he just put in that big G that we've been using, 6.674 times 10 to the -11, and that worked. So Coulomb's law and Newton's law of gravity are really unique in that they look almost identical, and they're completely different ideas. One has to do with how masses attract each other, and the other one has how charges either repel each other or attract each other. And so it's pretty neat that the equations look exactly the same. And so the great thing, one of the things I think that what reason why we're doing this now is because of those two equations are so close. Plus, then charge is really, really small, and so you're going to see that we're going to use scientific notation again, and mass is really, really big, and so that's why we're working on keeping you guys comfortable putting all those equations into your calculator. So Coulomb's law, F is equal to K times the charge, Q1, times the charge on the second object, Q2, divided by the resistance squared, or no, the distance between them squared, or R squared. All right. And so K is a constant, 9 times 10 to the ninth. I know a lot of you guys were worried about the units for the constant, but the units for the constant are just so that we make sure that we get a unit of force when we get done with this calculation. So don't worry about the units for the constant. They don't change anything. They're the units. This is the number 9 times 10 to the ninth. Okay, and then here's Coulomb's law. So let's do an example. So I'm going to hopefully get this off and get the camera on. There we go. All right, so how do we do Coulomb's law? So let's say we had a problem and they said we want charge, we have two charges, one's 5 coulombs, the other one is 3 coulombs, and we're going to put them 2 meters apart. Okay, and so if we have these two charges and we were to draw it out like that, right, we would have a charge here of 5 coulombs, we'd have a charge here of 3 coulombs, and they would be 2 meters apart. And so there's nothing that we need to do. These numbers are in coulombs, so that's the unit for charge. This is in meters. That's what we wanted in. And so we just write down Coulomb's law, and we say, okay, what's K? K is always a constant, 9 times 10 to the ninth, times Q1. It's the charge on the first one, so that's 5, times the charge on the second one, that's 3, divided by the distance between them, 2 squared. Okay, and it's as simple as that, and that's Coulomb's law. And we can calculate the force using that. So there's another one right here, but this time using the real number. So this is like the actual numbers instead of just coming up with a charge of 3 coulombs is a really, really big charge. And so when we think about how small these particles are, these numbers are going to be really, really small. And so their actual numbers for a calculation like this would be more likely 5 times 10 to the negative fifth. Okay, and so what we have here is the same idea. We've got a charge here. Charge number 1, this is Q1. Charge number 2, Q2. This one is negative 5 times 10 to the negative fifth. This one is positive 3 times 10 to the negative fifth. All right, and the distance between them is 0.002 meters. All right, so if we drew that out, it would look like that. And we would know that these two charges, because one's negative and one's positive, would be an attractive force, that these would be pulling towards each other. And so to calculate, all we do is just say, well, F is equal to K, Q1, Q2 divided by R squared, where we say that, well, K is 9 times 10 to the ninth. All right, Q1 is negative 5 times 10 to the negative fifth. Q2, the charge is 3 times 10 to the negative fifth, divided by 0.002, and we square it. And that's how we use Coulomb's law. All right, so you guys can start the practice, and I think there's enough there to keep you busy. And don't worry about turning in Coulomb's law practice. That's going to be something that we're going to continue working on Tuesday. Thanks for all your work today, you guys, and I hope everyone's doing great, and I will see you tomorrow.